By using current symmetry, see how many variables could be reduced. 1, 2, 3, 4. 4 resistors, 4 currents. But we used just one, I double dash. 1, 2, 3, 4. Again 4 resistors, 4 currents. Just one, I dash. So current symmetry is a very powerful method. But you have to be absolutely sure about watching from here from the beginning till the end, is it the same? There should be no difference at any point. Only then you can say I dash, I dash. I double dash, I double dash. These two. There is no reason why these two should have different currents. Likewise, working from the right side, working from the left side approach. Right side looks like the left side. So these two, like these two. Now look at this junction. There's a soldering there, physically, really. But whatever comes, goes. These wires are so good friends that they don't talk to anybody else. Even though there is a group of 6 people, these two don't talk to anybody else. So it is as good as no group, but only these two talking to each other. No shares, no contribution. Whatever comes, goes here. So why do I need to show a junction, even though there really is? I don't need to show it. If I just lift it, I don't violate the laws. I don't violate the nodal law. So how about lifting it? How about lifting it? Let them talk to each other. And likewise, these two also are like that. No contribution to the node really. Whatever comes just goes. So they are keeping to themselves, not talking to anybody else. So let's remove them and keep them together. It makes no difference. It makes no difference to what is actually happening. In spite of a junction, this is what is actually happening. If you have any question up to this point, let me know. It may be a good idea to try this problem using potential symmetry methods on your own after the class. And you will realize that across this line, that's the mirror across which you watch for potential symmetry. You will find that these two will sit over each other. These two will sit over each other. You will be able to bend about this axis of rotation. This will act as axis of rotation. This will lie over it. This will lie over it. When you do by that method, you will be able to simplify to quite an extent. But eventually, you may have to resort for some approach which we have used in this current symmetry method. Or you can use potential symmetry with star-delta transformation or delta-star transformation. That can work. Now, we opted for current symmetry, and now you see at this point how easy it is looking. Even though we used variables I dash, I double dash, but we won't need to write a single equation to answer the overall resistance. You don't need to write a single equation. These two are in series. Two are in parallel with R. Then that equivalent in series with these two. Series, parallel, overall in series. These two in series, and then upper, lower, middle, all in parallel. So simple. Can you proceed further and see what answer you get? Let me check. That's correct. 4 times R divided by 5. How about 3-dimensional problems? Here, geometry actually does not matter if we are not taking into account the length. If you are not taking into account the length, then the actual geometry won't matter. So whether you have a network of resistors in 3D or in 2D, in fact, look at this problem that we discussed, that we have here on this board. If you watch it carefully, you can notice that it is a tetrahedron. So, what's the difference? Whether I call it tetrahedron or I don't call it tetrahedron. Its geometrical orientation in space, how does that affect our working? We will still say, whether it's tetrahedron or not, that this is a balanced Wheatstone bridge to cut this resistor. So many 3-dimensional cases can be converted to 2-dimensional cases, and then you can solve. And sometimes it may be convenient to visualize in 3 dimensions only. It's a matter of what looks more convenient, easy. So, supposing we have this problem. You can imagine a battery connected across these 2 points. I have not shown the connecting wire. Now, each edge has resistance R. Each edge has resistance R. Supposing we first try the two-dimensional approach, right? Convert three-dimensional drawing to two-dimensional drawing. Suppose we try that approach. How about this drawing? Ignore the length of the edge. I mean, resistors are all equal. Imagine watching it from the top view. Look at that. That's a two-dimensional drawing. Isn't it the same? How many edges were there? 12. How many edges are here? 12. The question is of convenience. And which are the 2 points? That's very important. Which are the 2 points? Okay, I think 1 point is at the terrace, 1 point is at the floor. One at the terrace, one at the floor. Okay. That means it should be like this. 1 point at the terrace. This is the terrace, you can imagine. This is the floor, you can imagine. 1 point on the floor. So you have to find the resistance across these 2 points. So let's see if it is convenient or not, working like this. You can see about this line of symmetry. That left and right sides are identical. Left and right sides are 100% identical. If this point is plus, that point is minus, potential falls gradually. Highest at plus, lowest at minus falls gradually as one goes from plus to minus. But these points should be at the same potential. These two follow identical potential. Then what about these two? Why should they be at different potentials? If 2 points are at the same potential, you can keep one over the other. It's the same. Join them. That means about this axis, we can rotate the right side, or let's say we fold the two. This fellow will lie over this fellow will lie over this. You will see several advantages of that. This resistor will lie over this resistor. They will be in parallel, right? That means R by 2. Deleting this fellow. This is gone. This is R by 2. Then, when we do this bending, this fellow will lie over this fellow. That means this fellow will become R by 2. This will be gone. This will overlap with this. This will become R by 2, this will be gone. This will overlap with this. Parallel R by 2, this is gone. This will overlap with this. Parallel R by 2, this is gone. Then this fellow is still R. That will be R only. That fellow will be R only. Any questions if you have up to this point, let me know. Whatever resistor folds over the other, this will be lying over this. So these two will be parallel. 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 If one resistor lies over the other resistor, they will always be parallel. Now, this R and this R by 2, what type of connection is that? That will be series connection. This is gone. That means this is R plus R by 2. 3R by 2. This is 3R by 2. How about these two, R by 2 and this R? That also series. I think we will need to do some drawing now. Things have become quite short. R by 2 at the top, then this 3R by 2, first these 2 points, this point and that point, this R by 2, this R by 2, this R by 2, this is that R by 2, this is 3R by 2, this is R by 2, that is 3R by 2, Now, across these 2 points, while it may look like Wheatstone bridge, 3R by 2, this is R by 2, R by 2, 3R by 2. This is not Wheatstone bridge. This is not Wheatstone bridge, but there is a result for this. When we have something like this, R1 by R2, R2 by R1, R3. Shape may look like Wheatstone bridge, but it does not fulfill that condition. Then the resistance is given by it's gone by this. Now put these values R by 2, R by 2 and R by 2. And see what answer you get. Well, the answer I have is 5R by 6. Check your working. This will have to be rechecked. Okay, there is one thing. Actually, I converted the formula for capacitance to resistance. So 1 upon should also come. Let me check the values. I may have to check earlier, but see if you are also getting 12 by 7. If you are getting something else, let me know. After double checking. Okay, I think there is one correction in this formula. It is 2 by R3. So 2 R1 R2 that will make it 10 R square that means 10 by 12, which is 5 by 6. Actually, I use this formula for capacitors C1, C2 and C3 type of situation. C1, C2, C3, C2 and C1. And for capacitance it is twice C1, C3 plus C2, C3 plus C3, C1 divided by C1 plus C2 plus twice C3. So this is what can be done to convert a capacitance formula to a resistance formula. Just go for reciprocal. Capacitance and resistance have reciprocal relationship. In fact, we discussed some conversion also, star delta or delta star in capacitance. Of using that, if you just put 1 upon for all capacitors, you will get the formula for resistor. It's a very powerful, so to say, short technique. However, this method, speaking generally, did not prove a short, a quick method. So we go for another approach for this problem. If you have any questions up to this point, let me know, or I go for an alternate approach. The two-dimensional conversion method that we used, in that eventually we used potential symmetry. So how about trying current symmetry? Looking from here till the very end, see if you find differences in the three roots. There are three roots, but till the very end, if you find differences, see if you find any differences. How the current will go via these different routes. This is the diagonal. So it looks like a nice symmetry here. Let me make it dashed. It looks like the three paths for the current are identical paths. Current has no reason to favor one path over the other path because of the diagonal behavior of the circuit. Battery is connected across these 2 points. Now that will make our job really easy. If I current enters, I by 3, it's all I by 3. Now if you watch from here, and you watch from here, you don't really find any difference. So if I by 3 is here, well, same 3 fellows, 1, 2, 3 fellows, I by 3, I by 3, I by 3. Now once I by 3 reaches here, it will think again, should I prefer one particular route over the other? So what is wise for the current to do? Is it getting some less resistance route, or to reach from here to here, all routes are identical? To go from here to here, looks like all routes are identical. This is the diagonal. So why one route will have lower resistance than the other, no matter where you go? So it looks like identical situation here again. So I by 3 will break up into 2 pieces. I by 6, then I by 6. Well, here we did not have to introduce any I1, I2, etc. So it's a simple problem, I would say, by this method. Now choose any path, call it AB, VA minus VB is equal to VA minus VC plus VC minus VD plus VD minus VD. VA minus VB is V, where battery is connected. VA minus VC is I by 3R, I by 6R, I by 3R. Just find V by I. V by I is called resistance. I mean overall resistance. If you have any questions regarding this method, then let me know. And you would have realized different approaches can mean so much to different problems. If you view this as a tetrahedron problem, then a two-dimensional approach makes it so easy. But when we tried potential symmetry after 2D conversion, it was not very convenient in comparison to current symmetry method. This one. Any question concerning this, let me know. If there are no questions, then we stop now.